All right, so I'm gonna go over the PowerPoint that accompanies the chapter 2, the chemical foundation of life. This is meant to help your understanding, not replace you reading the textbook. You will have a reading assignment to go along with that. All right, so let's get started. Atoms are the building blocks of molecules, so life is composed of matter. Matter has mass, it occupies space. You probably remember this from previous classes. And elements are unique forms of matter. They have specific chemical properties, specific physical properties. So those chemical and physical properties would be unique to that particular element. Elements cannot be broken down into smaller substances, and yes, they are composed of smaller things, the subatomic particles, but individually those particles don't have the physical properties of the element. So, and then each element has its own unique chemical symbol. So like, for example, sulfur is S, calcium is Ca. Whereas carbon is C. Well, that's why calcium has to be Ca, because they both can't be C. Oxygen O, hydrogen H, nitrogen N. And then carbon, oxygen, hydrogen, and nitrogen are the four most common elements in living organisms. It doesn't mean that's the only elements we find in living organisms, but those are going to be the most common ones. And let's take a look at how that breaks down as far as comparing the amount of oxygen in, like, let's say humans. So 65% of the elements in humans is oxygen. And then in the atmosphere, it's only 21%. It's like a third of that, what's found in humans. And then the Earth's crust is 46. And then you can see carbon is 18, and then its trace amounts in the atmosphere and Earth's crust. Hydrogen and nitrogen. Nitrogen gets a little small. It actually kind of switches with nitrogen. You know, we only have about 3%. Atmosphere has about 78%. Just to give you a comparison of living to non-living substances. So we already talked about elements a little bit. So the smallest part of an element that retains all of that, the chemical properties of the element, is an atom. We would consider that our smallest unit of matter. When we look at we look at how an atom is made, you're going to have a nucleus. You're going to have a nucleus that's going to be composed of protons and neutrons. I'm just going to draw some very bad circles here, of course. And then around it, orbiting that, are going to be your electrons. I'm going to do those in blue. So you'll have, I'll make them a little bigger so you can see them. And these are going to be very small particles, and they're going to be orbiting around the nucleus. And collectively, these are called subatomic particles, where the word sub means below. So they're below the atomic level. And then just another comparison. We already talked about the protons and the neutrons are in the nucleus, and the electron orbits around. Protons have a positive charge. You might sometimes see just plus, and electrons is negative. This becomes important because when you try to figure out the overall charge of the atom, you have to add up the number of protons and electrons. Your proton number is always going to be a positive number. The electron is always going to be negative. So that way, if you add them and you get a negative number, then you know that the atom has a negative charge. If you get a positive number, then it's a positive. And if you get 0, then it's neutral. And neutrons, you see here, are neutral. That's why there's a 0 there. And then the atomic mass unit, I do want to point out that, yes, this says 0, and electrons are parts, you know, they are made of things, they do have mass, but it is so small that it doesn't really factor in. So when we calculate the mass of an atom, we're only using the protons and neutrons. So the atomic mass is equal to the number of protons and neutrons. And then again, here's a much better picture than what I tried to draw of the arrangement of the atom. So we're looking at a helium atom here, and you see that there are 2 electrons orbiting. So you have one here and you have one here. And then in the nucleus, we actually have 2 neutrons and 2 protons. And because the number of P equals the number of E, then you have +2 for the protons, and then you add that to the -2 for the electrons. So that gives us an overall charge of 0. So this is a neutral helium atom. And again, this is a simplified version of this. We don't get into a lot of chemistry stuff. It's very basic in biology. And maybe some of this is a review for you if you've taken chemistry before. If so, then fantastic. If not, then my mini crash course here. So atomic number versus atomic mass. So the atomic number is the number of protons. Every element has a distinct number of protons. The number of protons does not change. Where the atomic mass is equal to protons plus neutrons. Now, this also takes into account the isotopes. So like the different isotopes for carbon. You have carbon-12, carbon-13, carbon-14. So when we look at carbon on the periodic table, when we look at the atomic mass, there's some decimal places. And the reason for that is it's an average of all of the isotopes. So we're going to round up for it. I'm not worried about extra decimal places or, because you can't have 0.2 of, if you're figuring out the neutrons, you can't have 0.2 of a neutron. So we need to round it up. And again, we're not including the electrons. If we're doing the atomic mass, it's protons plus neutrons. And protons equals the atomic number. So just looking at the periodic table, you can figure out so many things about these atoms. We're going to get into this a little bit more. All right, so still talking about atomic mass and atomic number. So here's our chemical symbol. This is for carbon. Its atomic number is 6. And down here is the mass number. So this is actually carbon-12. Carbon-12, these are the 2 stable isotopes. Carbon-14 is not very stable. So when we talk about the mass, it's approximately 12. So if we know that the atomic number says there's 6 protons, then that means we know that we have 6 neutrons. And then again, even for isotopes, the proton number does not change. It's what changes is the number of neutrons. So in carbon-13, it still has 6 neutrons, but its atomic number is 13. So 13 minus 6, which you probably already did in your head, that gives us 7 neutrons. So we have 6 protons, 7 neutrons in carbon-13, 6 protons, 6 neutrons in carbon-12. Still going into isotopes. So we're looking at different hydrogen. Oh, my mind went blank for a second there. So we're talking about this first one here. We have 1 proton, 1 electron, no neutrons. Again, they each only have 1 proton. So that's our protons. And then this one's going to have a neutron. I'm just going to kind of squiggle some green on here. So these are our neutrons. Whoops, that is supposed to be an N. Maybe by the end of the semester I'll get better at writing on this. Probably not though. But just to compare, and then they have different mass numbers. So if this only has 1 and this has a mass of 1, this one has a mass of 2, this one has a mass of 3, because there's 3 things contributing to the mass. Remember, the electrons don't add anything. In the actual PowerPoint presentation, you can click on this and play around with it. The virtual simulation is pretty nice, so you can kind of see how it plays out with the isotopes. Isotopes can be used for figuring out the age of certain things. You've probably heard about like carbon dating. So as they change, so these radioisotopes are going to emit neutrons, protons, electrons. So over time, carbon-14 actually decays to nitrogen-14. So we can compare how much carbon-14 is in the atmosphere, carbon-14 in the fossils, and estimate the age. We can do, for certain things, if this isn't practical, so we have to look at other isotopes like uranium, potassium, rubidium. But knowing the decay rate, we can figure out, if there's this much there, this is how much it should have started with, this is how old it is. And here's that lovely periodic table. So again, I kind of hit on this on one of the other slides. So let's look at this hydrogen one right here. So we have the atomic number, and they go, just to make sure, they go this way. And then you got to come back down and go this way. So here's 1, here's 2, here's 3, just to make sure that that's clear. But looking down here on this hydrogen, we have the atomic number, we have its symbol, and its name, and then the relative atomic mass. Now again, this has some decimal places because it's taken into account those 2 other isotopes. And when we were to, if we're going to calculate this, we're just going to look at, it as a 1. So if I said, how many neutrons does hydrogen have? You would do 1 minus 1, atomic mass minus atomic number, and 0, because 1 minus 1 is 0. I could do that with any single one of these. If we looked at, let's say, copper right here, it's number 29, so we know it has 29 protons. Hopefully you're saying this along with me, and I probably picked one of the worst ones because it's nice and small. 63.5, I guess, is what I'm going to say. So 64 minus 29, I'm going to have to do this. Maybe some of you are a little bit faster than me when you're doing this. What is that, 9? That's 5. So for this one, there's 35 neutrons. If I did that right, if it's 65, or 64, I mean. It's kind of small, but hopefully you get the idea. All right, so electron shells in the Bohr model. So this is the one that everybody's like, oh, it looks like a solar system. It's a very simplified version of where you can find the electrons orbiting the nucleus. So when an atom has a neutral charge, the number of protons equals the number of electrons. So therefore, the number of electrons equals the atomic number. So like carbon is 6. It has 6 protons, and it's going to have 6 electrons. Just as an example, that's one I know right off the top of my head. So this is the Bohr model is an early model with protons in the nucleus and electrons in the orbits at a certain distance. So we have these 1n, 2n, 3n. These are the electron shells, or the energy levels, the closest one and then farther out. They're always going to fill in the ones closest to the nucleus first and then fill out. The one that is on the outside is the one we're going to talk about in terms of bonding with other atoms, because atoms interact with each other, obviously, because we have molecules, right? So the outer shell is referred to as the valence shell. And the atom is most stable when it has a full valence shell. So if it has any vacancies in that shell, it's gonna react to try to fill it, whether it's gonna share electrons or donate or receive electrons. We'll get into in a moment, but what they want to do is they want to have a full outer shell. And if you look, like neon, this one is full, helium is full. So let's go on to my next slide here. So when the outer shells are filled, they're going to have 8 electrons. They want that outer shell, well, depending on what level it is. That first shell only actually holds 2. That's why you only see 2 right in here. I like this. I'm going to make a side note. I like to do the recording on the PowerPoint, but it kind of drives me crazy because it puts my picture right over part of the slides. All right, so Bohr models are incomplete. Electrons don't orbit like a planet. Like I said, that's very super simplified. They're actually, the orbitals have crazy shapes. They have, well, I don't want to say crazy, but they're not just clearly orbiting around like the Earth around the sun. Quantum mechanics allows us to predict where an electron might be, where it might be. So let's talk about where these might be. So the S subshells. So we have the S subshells. Within each Bohr model shell or subshells, the subshell S, P, D, F have specified number of orbitals that contain electrons. So they can only hold so many electrons in there. The S subshell is spherical and it has 1 orbital. The P is dumbbell shaped and it has 3 orbitals. And you can kind of see our planes here. We have our X, Y, and Z. So again, the S subshells are shaped like spheres, and both the 1N and the 2N principal shells have an S orbital. So that's the first 2 shells we were talking about in the Bohr model. But the sphere is larger in the 2N orbital, and each sphere is a single orbital. What I really want you to pull from this, because this is biology, not chemistry, is to understand that the orbiting the nucleus idea is not complete. It's helpful for us to visualize in terms of, kind of simplicity, and this puts, this model actually puts it, more realistically, but for the purposes of this class, we're going to really refer to it just as using that Bohr model, that very simplified version of the atom configuration. I'm not going to play this. If you want to go back into the, if you need a little bit more explanation and get some better explanation from this, if you're curious, you want to know more, sometimes knowing more is better. So let's get into the electrons, how they react, or really how they're, how many there are on that outer valence is going to determine if they interact with other atoms or not. Really, chemical reactions are just changing of where electrons are between atoms. They go from here, they go to there, they switch it around. I'm super simplifying some of it, but that's all right. So chemical reactions, we have our reactants. That's what we start with. This is what's a reactant. It might be one substance. Like in this case, this is hydrogen peroxide, H2O2. That extra oxygen makes it a completely different substance. And then the products are formed, and you tend to see them on the right side of this arrow. So in this case, we have the hydrogen peroxide being broken down into water and oxygen. And if you've ever put hydrogen peroxide on a cut or a scrape, or maybe you did a potato enzyme lab, but if you put it on a cutter or scrape, you'll actually see a bubble, and people get all excited. Oh, it's cleaning it, it's cleaning it. That's not what's working. That's not what's happening. What's happening is you have an enzyme that's actually going in and it's breaking the hydrogen peroxide apart. So what's not really shown in this is there's an enzyme in there, because we haven't gotten there yet, but I'm going to go on ahead and mention it. There's an enzyme breaking this hydrogen peroxide apart, and it makes it into water, which obviously is okay to your body. It's not going to hurt it. And the bubbling you see is the oxygen gas being released as a product of this reaction. Got a little tangent there. So if you have an irreversible reaction, you're going to have an arrow going a single way. So that was our peroxide to water and oxygen gas. Sometimes they can go back and forth. And then you'll have an arrow pointing both directions, meaning it can go this way to produce this, or that can be broken to produce this. So it can go back and forth, and there's probably more than what we're going to talk about, but just so that you know. All right, let's get into the chemical bond. So there's an attractive force that allows the atoms to form molecules. So instead of just being single atoms, they can bond either with atoms of their own element or atoms of different elements to form molecules. So we're going to look at some of the bonds here now. So covalent bonds, electrons are shared. Electrons are shared. You might have, so for instance here, let's talk about, this is one we're going to talk a lot about. Let's talk about water. So we have up here, we have an oxygen atom and 2 hydrogen atoms. And if you look, the hydrogen atoms each have a single electron. And they actually have space for a second electron in their single shell. Whereas oxygen actually has 6 electrons, but it has room for 2 more because it wants to have 8. So what it will do is it will bond with 2 different hydrogens. They will share the electrons, and now they both have, or all 3 of those atoms have a full outer shell, so they are more stable. When electrons are shared between atoms, it is called a covalent bond. Covalent bond. You can have more than, so we already talked about O2. O2 is that gas that was being given off as a result of the hydrogen peroxide being broken down. And in the oxygen atoms, again, they have 6. If they share 2, hey, I'm going to give you 2, you give me 2, and now we're stable. So this is a double bond. And you can have triple bonds. We're not going to get too far into that. I just want you to understand that that does happen. In ionic bonds, atoms give up, they donate, or receive electrons. So one of the main ones we always talk about for this is going to be sodium chloride. So NaCl, sodium and chlorine. If you didn't know, it's salt. So what happens is the sodium has a single electron in its outer shell. It has 7 vacancies. It's trickier to get 7 more electrons. It's easier to get rid of that electron. Chlorine only needs 1 more. So it will actually get its electron from sodium. And if you notice, because this lost an electron, now it has more protons. It has 1 more proton than it does electrons. So the sodium becomes positive. Whereas the chlorine now has 1 more electron than it does protons, so it becomes negative. And this is going to become important when we talk more about water properties, but let me go on to the different types of covalent bonds. So there are 2 types of covalent bonds, and the first one we're going to talk about, we already talked about water. What happens between the oxygen and the hydrogen is that the oxygen has a higher electronegativity. it says wants the electrons more than the hydrogen, but it's stronger. It's pulling the electrons more towards it. And when it does that, they're unequally shared. These electrons are not shared between this hydrogen and this hydrogen. They're not shared equally. And what happens is you have a little bit of a bent here, or bend in the shape, but this side becomes negative, and now this side is slightly positive. So this is called a polar molecule. And this is specifically, this is a polar covalent bond. There are actually two of them in water molecules. And then the other one would be a non-polar covalent bond. So let me skip to this one. Here we go. If they are shared equally, so in a covalent bond where they are shared equally, then it's non-polar. I'm going to look down here at the methane. So we have a carbon with 4 hydrogens. It shares the electrons very equally. So therefore that's non-polar. There's no charges. This is a neutral molecule. So when we say polar, we mean this one has charges on the ends, whereas non-polar, there's no charge. This is a neutral molecule. And then you also see carbon dioxide down here as well. So the way it's spread out, it's also non-polar. All right, so we're going to talk about a polar compound with a non-polar compound. This is just an example of it. So you have these water molecules, and they're going to actually form these hydrogen bonds with each other. So hydrogen bonds are not bonds in the sense of there's no electrons being shared. They're just attractions. And if you look, you know, the hydrogen side, that's these smaller ones. Remember, that has a slight positive, and this has a positive. So what's going to happen is it's going to be attracted to the opposite region. So the oxygen is negative. So this positive here is attracted to this negative, and so forth. And these are weak bonds that are formed and broken at the surface. There's a lot of them. The surface tension is an important water property, and we'll get into, but this is a great example of the poles, the charges interacting with the poles of the other molecules. Kind of lost my train of thought there. It's fine. So ionic and covalent bonds require energy to break. So they are strong. Covalent is even stronger, but the weaker bonds are the hydrogen and the van der Waals interactions. So the hydrogen bonds are going to be the interaction between a positive of a hydrogen and the negative of another atom on another molecule. It tends to be oxygen, nitrogen, fluorine. There's like certain ones that'll interact with more. But the one we're mainly going to talk about are the ones found between water molecules and the ones that are going to be found in the DNA where the nitrogen bases actually come together, but we're going to get to that later. And then the van der Waals interactions are just interactions between 2 or more molecules due to changes in electron density. We don't really get into those too much, really at all, in this class. The hydrogen bonds, the covalent bonds, the ionic bonds, particularly covalent and hydrogen as they relate to water, are the ones we're really going to get into. So I could have asked you this, hey, you know, why is water important? You know, it makes up most of our body. Life as we know it is water-based. So when scientists go looking for life on other planets, that's what they're looking for. They're looking for water, specifically liquid water. But that doesn't mean, I'm not going to say that it rules out the possibility that life might not need water, but we go with what we know, and what we know is life here requires water. So 2 of the major things, really, if you want to boil it down to one thing, because of that unequal sharing of the electrons when the hydrogens bond to the oxygen, causing it to be a polar molecule. That's what makes water so special. And then because of that, it can form hydrogen bonds. And let's talk about hydrogen bonds a little bit more here. So remember, the covalent bonds in the water molecule made the polarity. I already talked about this a little bit. You have this negative charge on the oxygen side being attracted to the positive charge of the hydrogen side on a different molecule. Now, note this molecule, this water molecule in the middle, is actually formed several hydrogen bonds with different molecules. I mean, these two over here are attracted to the same, their hydrogens are attracted to this oxygen over here. So again, these are weak bonds, but they're strength in numbers. So the more there are, the more they hold on to each other, especially at the surface. And even though these bonds, as the water molecules are moving around, they're broken and reformed, they keep the water together. Let's talk about a few of these, the three major states of matter for water. Liquid water, hydrogen bonds are made and broken and remade. When the water is heated up, when it has enough energy, and it has to have enough energy for those bonds to be broken, then the water molecules can escape into the air as gas, but that's breaking those hydrogen bonds so that they're individual, or not as clumped together. I mean, I don't want to say it's every single individual little water molecule. That's not the way it works. And then solid water, the temperature gets lowered and the hydrogen bonds will actually kind of push each other and spread out. Most things, when they go into their solid state, they actually contract. Metal is a great example of that. As it heats up, it will expand. And if you've driven across a bridge, one of the major bridges in this area, you've probably seen some of they have joints where they'll go like this, and it allows the bridge to contract and expand without being structurally unsound. So in the winter, when it gets cold, it's gonna, kind of contract in on itself. And as it gets warm in the summer, it's gonna expand and be able to go that way. But water doesn't do that. So hydrogen bonding makes the ice less dense, which is why ice floats. The water molecules actually spread out. They do this nice little lattice structure. When I say less dense, I mean if we were to look at the same area and we could zoom in and count the water molecules in the same size or same amount of ice versus liquid water, you would find more molecules in the liquid water because they would be closer together. In the ice, they spread apart. And this allows for water to not freeze solid. It also means that the ice is just going to float on top rather than forming, being too heavy and sinking. And then you have another layer that sinks and another layer that sinks. And eventually it's going to make that body of water solid and nothing can live in there. There's a great video here you can watch. I haven't clicked on it to make sure it works, so let me know if it doesn't and I'll find something else. All right, so heat capacity. Specific heat capacity is how much heat 1 gram of a substance must absorb before it changes temperature or raises the temperature into 1 degree Celsius. Water has a high heat capacity because it takes a lot for water to heat up and a long time for it to cool down. Even as we're still in the warmer kind of summer weather, but even as we start to transition into the colder fall and winter weather around here, the Chesapeake Bay, the ocean, maybe if you have a lake in your neighborhood, that water temperature isn't going to shift as rapidly. If you were to measure the water temperature every hour for, let's say, 2 weeks, there'd probably be some fluctuations depending on the weather around us, but it's not going to change as much as, say, the air temperature. The air temperature, we all know, you leave in the morning to go to school, you come back home and it's different, So the air fluctuates, but water actually can retain its heat, and that's actually important because it helps to regulate temperature. For us, just being made of water, it can help us to maintain a stable body temperature. Even though we create our own body temperature, it still helps to maintain it. It also means that aquatic environments are not going to fluctuate as much. That's going to help the things that live there. And then we get into high heat of vaporization. So the difference between specific heat is you're making, changing the temperature 1 degree Celsius, but heat of vaporization is the energy required for 1 gram to go from a liquid to a gas. So even to change states, solid, liquid, gas, water needs a lot of energy, and it really goes back to those hydrogen bonds. They're weak, but they're strength in numbers, and especially at the surface, there's a lot more of them there. So it takes a lot of energy, which again keeps fluctuations from happening, crazy fluctuations from happening rapidly. And then water can dissolve many things. So water is a solvent. It does the dissolving. Anything that we mix and dissolve into it is the solute. So if you are making Kool-Aid, the Kool-Aid would be the solute, the water would be the solvent. And if you had to add sugar, because most of them, if you don't get the bigger container, you just get the little Kool-Aid packets, you have to add sugar. So that would be another solute. So ions and polar molecules can dissolve in water. Non-polar molecules do not dissolve in water. You might be able to mix them into a suspension, but they do not dissolve. There's things like oil. Oil and water don't mix, and that's why, because water is a polar molecule and oil is a non-polar molecule. So they are not attracted to each other to mix. All right, water can make hydrogen bonds with other polar molecules. So if you were to put salt into water, so sodium chloride here, the atoms break off and form ions. So remember, we talked about this earlier, because when the sodium and the chloride interact, the sodium says, here's my electron. Now the chlorine has extra, so it's negative. So if you notice, this is negative, so the positive hydrogens are attracted to it, whereas the sodium is positive, so the negative oxygens are attracted to it. And that's how it can, pull them apart, and it actually makes little rings around them, around the ions. And then we have cohesion of water. Cohesion is water sticking to water. This is the hydrogen bonding. This is just another way to say that, water forms hydrogen bonds with itself. Anything that anything that sticks to the same thing, it's cohesion. It's like molecules sticking to like molecules. So like in a raindrop, the more molecules stick together, the bigger the raindrop. It's also why if you fill up like a shallow dish and you filled it up, you could fill it up so it's almost overfilling. And it looks like it's about to bubble, but it'll hold on to it. One of the popular lab activities for this is the drops on a penny. You get a penny and you put so many drops in there, and you can actually, if you actually lean down and look at it, you can see it kind of bubbling over. And eventually, yeah, it'll get too much and it'll go over the side, but it can hold quite a bit. So cohesion, I've mentioned surface tension a couple times. So surface tension is really the tension at the surface that allows things to rest on. I'm looking for a piece of paper. So if this is the surface of our water, you can see me in the video, and you have something just resting on it, just pushing into it. So the surface tension still holds it up. It's not in the water, not like the ice was floating kind of in and out, or if you're floating in a pool or the ocean and you're kind of in and out of the water, you're not being kept up by the surface tension. Light things like a needle, some insects can take advantage of this. And you can actually, if you look very carefully, you can kind of see a little indentation here, because like I said, it's on the surface, it's not in the water. And this again is the hydrogen bonds, and because there's a lot of hydrogen bonds there, it helps to keep the water from changing temperatures too rapidly. All right, capillary action is another good one here. So this is actually by two things going on. So we already talked about cohesion. So the water sticks to itself, but it also sticks to other things. And this is adhesion. And this is why when you take measurements and you're looking at a graduated cylinder, you have to look at that bottom part of that meniscus, why the water curves, is because it's sticking to the side. Now in a capillary tube, a very, very thin glass tube, maybe you've gone to the doctor and they use it to test, like for iron. They'll prick your finger and they'll put the tube there and the blood will actually go into it without them doing anything. So the capillary action is the attraction of the water to the glass tube and the water to water, and it will actually move the water up the tube with no energy needed. And this is the way that plants are able to get water from their roots to their leaves without using energy. And when you think about giant trees like the great redwoods, no energy to move that water from their roots to their leaves, which is great because that allows them to be taller. All right, here's another, here's a bug on the surface. You can kind of see the indentations here, just to kind of see. All right, and now we're going to talk about pH. So pH indicates acidity or alkalinity, so if it's acid or base. This is our equation here. We have the water separating into, this is our hydrogen ion, H+. It's really just a proton because it's a hydrogen atom that's lost its electron. Where does the electron go? Well, it's over here with this hydroxide ion. So hydroxide ions and hydrogen ions. And we talk about the concentration. You know, if you know pH, I'm sure you've done this before, you know that pure water is neutral. And the reason why pure water is neutral is because the concentration of hydrogen ions and hydroxide ions are equal. If it has a higher hydrogen ion concentration, they are acidic. If they have a higher hydroxide ion concentration, then they're alkaline or basic. So let's look at our pH scale. Now a pH scale is just, it's there to compare the relative strength of each substance. So let's say bleach. Bleach is on this scale at 13. It is not a base because it's 13. It's a base because it releases hydroxide ions. And it's a stronger base because it's further away from neutral. So our neutral is here. Distilled water is our neutral, equal OH negative and H positive. And this is a logarithmic scale. So we actually get 10 to the negative 7. And really what I want you to understand is that this is just comparing. So we know that compared to ammonia, bleach is a lot stronger. So we have 10 to the negative 11, 10 to the negative 13. So again, this is showing you the relative strength of them. So our stronger bases are going to be closer to 14, and our stronger acids are going to be like 1 or under 1. So these are our acids are below 7, and our bases are above 7. And again, neutral is at 7. So even if it was like 7.5, it'd still be basic. It would just be very weak, very weak. So your body is constantly maintaining its pH, and regardless of what any water company with their alkaline water will try to tell you, you can't change it. You don't want to change it anyways, because if you can't have your pH stay where it's supposed to be, then your enzymes can't work. If your enzymes can't work, then certain reactions aren't going to occur and you're going to die. So this is showing you how buffers, allow this to go back and forth, to allow the process, if we need to lower, if we need to raise, it's talking about adding, sodium bicarbonate, or bicarbonate to it. So carbon dioxide, CO2, actually makes can make you more acidic. It's one of the reasons we exhale it, because we don't want to keep it in there. But your body can actually regulate that a little bit with buffers, so that way it's not just having to exhale it. We can change it. We can break it down and change the pH there. All right, let's go to the next one. So talking about carbon, talking about how it's important. It's the key component of macromolecules, also called organic compounds. I'm just going to write organic. You can write compounds in your notes. So carbon is unique. It can bond with up to 4 different atoms. Covalent bond, it allows it to be a backbone for macromolecules. It has 4 electrons in the outer shell. It wants to fill. It wants to get to that octet rule. So again, up to 4 covalent bonds, depending on how it's bonding. So hydrocarbons, they have carbon and hydrogen, such as methane. These, the covalent bonds between them are storing energy. When the energy is released, when these molecules are burned, and this energy release can heat our homes and power our cars. So that's how that works, in a simplified version, I should say. So methane has a carbon atom here, and then again, it has 4 hydrogens that it's bonding with to get to that octet rule. And then tetrahedral geometry, we're getting a little bit more into the chemistry of it, but allows them to be spaced 109.5 degrees apart. So we have hydrocarbon chains, we have tetrahedral, single bond here. Ethane is also tetrahedral with a single bond, and ethane is planar with a double bond. This is really just showing you different things. I'm not going to get too far into these. Just understand that this is one of the ways that carbon is so versatile. It's found in so many things that we use every day. We probably don't even realize it. So you can also have rings. Carbon can do these lovely little rings. You can have the 5-ring, the 6-ring, benzene in particular, using amino acids, cholesterol derivatives. Like I said, I'm not going to spend a bunch of time on this, and also I just realized how long this video is. So isomers, we have molecules that have the same chemical formula, but they're arranged differently. So if we actually broke down the chemical formula of butane and isobutane here, they have the same number of carbon and hydrogen atoms, but they're arranged differently. And then we have structural isomers, have a different covalent arrangement. Geometric isomers, different arrangement of atoms around a double bond, so they have this double bond here. And then anti-amers. Oh, my brain is not working now. I'm not too worried about you knowing, like, don't memorize all these, just understand that isomers, molecules can have the same chemical formula, but their arrangement's going to be different, which is going to have them interact differently. We have trans versus cis configurated here. Carbons are on opposite sides of a double bond, whereas in a cis configuration, the carbons are on the same side. So we have these hydrocarbons that have, these chains. Fatty acids are double bonded with unsaturated. I don't want to spend a whole bunch of time on this. This is just kind of extra information. Really, the important thing is to understand how they bond. We're getting really more into chemistry than we need right here. I'm not even going to worry about that one. Functional groups. These are going to getting into, especially when we get into amino acids. So each of the 4 types of macromolecules has its own set of characteristic functional groups. And these are groups that have consistent specific properties to these molecules. And these are going to interact with other functional groups via hydrogen bonds. And then just kind of talking again about hydrogen bonds, we have our, we actually have a small section of DNA here. This is our sugar phosphate backbone on one side, this is the other side, and then we have these nitrogen bases in the center, and then these little dashed lines are our hydrogen bonds that are holding these nitrogen bases together. So when you think about that twisted ladder of the DNA, holding everything in the rungs of those ladder are these hydrogen bonds. And again, they're rather weak, but they have strength in numbers, and it's going to become important when we go to replicate the DNA. We need to open it up quickly and be able to put it back together quickly. So that is the function for that. And I know I kind of rushed through these last few slides. Like I said, I got a little bit more into chemistry than I really wanted to, but it's great information, especially if you're interested in the chemistry. Hopefully this helped a little bit with your understanding. Make sure you go back and read Chapter 2 and be able to get into the Chapter 2 reading assignment. And of course, as always, if you have questions, email me.